Nonparametric methods are general methods of probability density estimation based on existing data without an assumption about the functional form of the density function. In this lecture, we will discuss histogram methods, kernel-based methods, and k-nearest neighbors. In histogram methods, attributes are scaled to the range from 0 to 1 or standardized to -1 to 1. Log transformation may be applied if small values are disproportionately close together and large values are spread. And exponential transformation may be applied if large values are close together and small values are apart. Then the histogram can be constructed using B bins. In each bin, there are n training instances and kb instances or points fall inside the bin, and the bin height is equal to kb divided by n. The value of b is crucial. If b is too small, then you may get noisy density model, and if b is too large, then it may wash out the nature of the underlying distribution. So b should be chosen reasonably. Suppose that a number of observations were drawn from some unknown probability density p of x. Let's consider a small region R containing x. The probability mass associated with the region is given by the integral of p of x within the region. For a small region and for continuous p of x, the probability is approximately p of x times v, in which v is the volume of the region R. Assuming that we have a data set with n observations from the density p of x, each instance or each point has a probability p of falling within the region R. So the total number k of points that lie inside the region R is distributed according to the binomial distribution, and n here is the number of instances or the number of points, and capital P is the probability of falling within the region R. From there, the expected value of k is equal to n times p. And the variance of k is p times 1 minus p times n. And from there, we can see that the mean fraction of points or instances falling inside the region is e of k divided by n, and which is p. And the variance of k divided by n is actually p times 1 minus p divided by n. For large n, the variance is smaller and smaller, and the distribution is picked around the mean. So k is approximately equal to n times p. And previously we had p is approximately equal to p of x times v. So the estimate for a probability density function for a given instance x, p of x is equal to k divided by n times v. The kernel-based method is based on fixing around a pattern vector x or instance x, a region R with a volume V, and counting a number of k of a given chaining patterns or the chaining instances falling in this region by using a kernel function, which is also called a pattern window, associated with the region. The estimate result can be exploited in two different ways. So we can either fix k and determine the value of v from the data, and that leads to the k nearest neighbor technique, or we can fix v and determine k from the data, and that leads to the kernel approach. Let's consider the region R to be a small hypercube centered on the point x, at which we want to determine the probability density. The volume of the hypercube V is equal to h to the d. H is the length of the edge of each edge of the hypercube, and d is the number of dimensions of the hypercube. We define a kernel window function k of u. U here is a vector. K of u is equal to 1 if absolute value of u sub I is less than or equal to 1/2 and 0 otherwise, and I is equal to 1 to the number of dimensions d. This window function is also called a pattern window. From there, it can be seen that k of x minus xn divided by h is 1 if the data point xn lies inside the cube of side h centered on x and 0 otherwise. Taking the sum from 1 to n to capital N, we have the total number of patterns or points or instances falling within the hypercube. Replace k in the approximation for the density in the previous slides, and also v, the volume of the hypercube. We have the estimate of the probability density function. The kernel density estimator suffers from discontinuities at the boundaries of the cubes. We can get a smoother density by choosing a smoother kernel function. The kernel function must satisfy the two conditions as given. And the common choice for the kernel function is the Gaussian, which then gives the estimate of the probability density function p of x here. This is the illustration for one-dimensional Gaussian. Given that the kernel function is a one-dimensional Gaussian, k of u, the estimated probability density can be calculated. The pattern window method can be implemented as a neural network known as the probabilistic neural network. Assume that we have n patterns or n instances, each of which is a d-dimensional randomly sampled from C classes. The network has d input units, and each input unit is connected to each of the n pattern units, and each pattern unit is connected to one and only one of the C category units. The connections from the input to the pattern units represent the weights, and each category unit computes the sum of the pattern units connected to it. In the tuning step, for n patterns or n instances, each tuning instance is normalized by divided by the length. The normalized xjk value is stored as a width connecting the kth input unit to the jth pattern unit. Aj is set to 1 if the jth pattern or instance belongs to the class omega I. The steps are repeated for all the tuning set. This slide explains the variables in the tuning algorithm. In the classification step, a normalized test pattern or instance X is placed in the input units. Then each pattern unit computes the inner product to yield the net activation, net K. Now let's consider a Poisson window, which is a Gaussian. After several steps, you can get to an exponential e to the net k minus 1 divided by sigma squared. And here we utilize the normalization conditions that makes the first term and the second term both equal to 1. In the classification step, a test pattern is introduced to the model. In each iteration, the net activation is calculated by the pattern unit, and then each output unit sums the contributions from all the pattern units connected to it. And the class of the test pattern is the index that maximizes G sub I. This slide explains the variables in the classification algorithm. One of the difficulties with the kernel approach to density estimation is the parameter h is fixed. So in the regions of high density, large value of h causes over smoothing and washing out of the distribution structure. On the other side, reducing h to a small value causes noisy estimates. So the optimal estimate, the optimal value of the parameter h may be dependent on the location within the space, and this is solved in the nearest neighbor methods. Instead of fixing the volume V and determining K from the data, the nearest neighbor methods fix K and use data to find the volume V. The estimation of the density is as follows. Let the cell volume be a function of the test data. Then the density P of X can be estimated by centering a cell about the X instance, and then grow the cell until it covers K instances. As shown in the Poisson window method, the estimate of the density P of X is given as K divided by n times V, and V is the volume of the sphere. Suppose that there is a total of n points or n instances, in which there are nk points in the class Ck, such that the sum of nk is equal to the total number of points n. We now draw a sphere with the volume V centered on the test instance X. And suppose that the sphere contains k sub k points out of k points from class CK. Then the estimate of the density for each class P of x given CK is equal to k sub k divided by n sub k times V. Just like the case with unconditional density, and also the unconditional density was given in the previous slide. As the class priors, P of CK is equal to n sub k divided by n. From there we use Bayes' theorem to obtain the posterior probability. P of class C sub k given the instance x is equal to the conditional probability times the prior divided by the unconditional probability, and finally we get k sub k divided by k. So in order to minimize the probability of misclassification, we assign the test instance to class that have the largest posterior probability. The voting scheme can be also weighted by the distance. Ties may occur when the number of instances in each class are equal. Ties break. Ties can be broken at random or using nearest neighbor, or the value of k can be adjusted. And before calculating the distances, attributes should be scaled to avoid distance measures being dominated by some attributes. The parameter k controls the level of smoothing. If k is too small, then we may get a noisy density model. If k is too large, then it may wash out the nature of the underlying distribution. The figure shows the illustrations when k is too small and too large in the first and is the last panel. A good estimate is given in the middle panel with a moderate value of k. The nearest neighbor methods can be compared with the Kernel-based methods using the same example, in which h acts as a smoothing parameter. If h is too small, then we may get a noisy density, and if h is too large, then it may wash out the nature of the underlying distribution. A good estimate of the density is given in the middle panel with moderate values of h. The figure shows the two-dimensional views of the oil flow data, in which we have three classes. It can be seen that small values of k produce many small regions of each class, and large k leads to fewer larger regions. K nearest neighbor classifier is a lazy learner, and it does not build model explicitly, and the expensive cost it has for classifying instances.